Hello, welcome. My name is Gearóid Ó Lainn. I'm the established Professor of Electronic Engineering in the School of Engineering at NUI Galway. Today I'm going to talk to you about the connection between electricity and human function and how electronics is being used to tap into this connection to deliver new medical therapies. I call my talk The Body Electric. You may have seen some old black and white movies based on the novel Frankenstein, written by Mary Shelley in 1818. In the novel, a human, composed of different body parts of dead humans, is reanimated or brought to life by Dr. Frankenstein using electricity. The novel draws on the association between electricity and human life, which was known at the time. Our understanding of the relationship between electricity and muscle contraction was greatly assisted by the work of Luigi Galvani, an Italian physician, physicist and philosopher at the University of Bologna in Italy. In 1771, he discovered that the muscles of a dead frog's legs twitched when he touched two different metals between the nerve and the muscle of the frog. The two metals interacted by forming a small battery and applied an electrical voltage between the nerve and the muscle of the frog. Galvani discovered that there was a relationship between electricity and nerve function. He effectively built the world's first electrical muscle stimulator using an electrostatic generator and a Leyden jar, or capacitor as it's called today, used to store the electric charge generated by the electrostatic generator. Galvani carried out a series of experiments using static electricity and discovered that the application of the voltage between the nerve and the muscle triggered a contraction of the frog's leg muscle. So the nerves are the wiring system of the body. Information is passed along nerves to and from the brain using electrical signals called action potentials. So action potentials are key to human function. Without action potentials, we cannot walk, run, breathe, talk, etc. All excitable cells tend to maintain high concentrations of potassium ions, K+, and low concentrations of sodium ions, Na+, in their intracellular fluid, or the fluid inside the cell. The extracellular fluid, the fluid outside the cell, contains plenty of both ions, but more sodium ions than potassium ions. The cell membrane that forms the barrier between the inside and the outside of the cell allows the passage of both of these ions to some extent. The cell membrane has an active transport mechanism that brings potassium ions into the cell and expels sodium ions. This NAK pump uses energy to move these ions against their electrical and concentration gradients. At rest, there is a potential difference across the cell membrane of minus 70 millivolts due to the unequal distribution of charged particles on the inside and the outside of the membrane. This difference in charge across the membrane is measured as a voltage. The potential difference varies in the cells of different tissues, being anything between minus 60 millivolts and minus 90 millivolts. In nerves and smooth muscle fibers, it's usually about minus 70 millivolts, and for skeletal muscle cells, minus 80 millivolts. We see an important level, approximately 10 to minus 15 millivolts less negative than the resting potential. This level is called the threshold of excitability. Thus, an action potential is an electrochemical change that is propagated along the length of a nerve cell's axon. It is initiated when a threshold stimulus is applied to the nerve cell. The stimulus causes large numbers of voltage-activated Na+ channels to open and Na+ ions to enter the cell, causing a rapid depolarization of the membrane. Closing of the voltage-activated Na+ channels causes the depolarization phase to stop abruptly. The voltage changes that occur during depolarization trigger the opening of voltage-activated K+ channels. The loss of K+ ions from the cell causes the membrane to repolarize. After the action potential is generated, sodium-potassium pumps in the cell return the ions to their original locations. An action potential is referred to as an all or none phenomenon. If the applied stimulus is not sufficient for depolarization to exceed the threshold of excitability, as is in the case in stimulus 1, 2, and 3, then an action potential is not generated. If the applied stimulus is sufficient for depolarization to exceed the threshold of excitability, as is the case in stimulus 4, then an action potential is generated. It does not matter how strong the stimulus is, provided the depolarization exceeds the threshold of excitability. And when this happens, the action potential is always the same size and shape. This is what we mean by the all or none phenomenon. A very good example of how the sensory and motor nerves work is the stretch reflex mechanism. Within muscle, there are sensory organs called muscle spindles. These organs measure the amount and rate of stretching occurring in the muscle. This information is communicated from the muscle to the spinal cord via action potentials transmitted along a sensory axon. This sensory axon synapses with a motor neuron, with the motor neuron axon going to the muscle fibers of the muscle. When we're standing to attention and start to sway forwards, our calf muscle fibers will be stretched and action potential will pass along the sensory axon from the muscle spindle. At the synaptic junction in the spinal cord between the sensory axon and the motor neuron, a decision will be made to fire the motor nerve cell, which sends action potentials along the motor axon to the calf muscle to contract the muscle and thus prevent the stretching of the calf and to bring the person back into the upright posture. This interaction between the motor and sensory nerves occurs at the spinal cord. There is no communication to the brain required, so that it happens very quickly without conscious input from the person. This rapid response is referred to as the stretch reflex. The brain has a role in enabling or disabling the stretch reflex through a gating signal at the synapse through a descending pathway from the brain. If we're walking, we don't want the stretch reflex to occur, as it would interrupt the normal fluid stretching of muscles that occurs during locomotion. If we're standing still, we want the stretch reflex to be active. So the brain understands the context the person is in and activates or deactivates the stretch reflex as appropriate. When a stroke occurs, damage to the brain results, and in some cases this inhibitory control of the stretch reflex is damaged, and the stretch reflex is active both when we're walking and when we're standing still. So when we try to lift our foot upwards, we stretch the calf muscle. The stretch reflex kicks in and the calf muscle contracts. And as the calf muscle is much more powerful than the foot lifter muscle, it overcomes the foot lifter and the foot ends up in a lowered or plantar flex position. This condition is referred to as hemiplegic dropped foot or drop foot. We see here a person walking with right foot drop foot. Notice how their right leg does not lift and maintains a downward or plantar flex posture. Drop foot can have a very debilitating effect on the person and result in reduced walking speed and increased effort associated with walking. Thus, drop foot can have a big impact on the person's quality of life. So now that we understand how action potentials are formed, how do we take Galvani's findings and create an electronic medical device? If we apply a sufficiently high voltage across two electrodes, one on the skin surface near the nerve we're interested in, and the other electrode nearby, we can use Galvani's findings to trigger the generation of a series of action potentials and contract the muscle of interest. This is what W.T. Lieberson did in 1961 with the system shown in the figure to treat hemiplegic drop foot, a condition caused by stroke where one half of the body is paralyzed to some degree, and in the case of drop foot, the person cannot properly lift their foot on the leg of the affected side of the body. He built an electronic unit, the stimulator S, and had two electrodes on the positive and on the negative outputs of the stimulator. The negative electrode E1 was placed on the skin surface over the common peroneal nerve, which activates the tibialis anterior or foot lifter muscle seen in the figure. The technical term for this movement of lifting your foot upwards towards your shank is called dorsiflexion. The positive electrode E2 was placed on the skin surface over the tibialis anterior muscle, which is located on the front of the lower leg. The final part of the system was very clever. The heel switch K. Whenever the person is trying to dorsiflex, they lift their heel and the heel switch detects this and delivers electrical stimulation to the tibialis anterior muscle. And when their heel returns to the ground, electrical stimulation is stopped
and this process is repeated automatically throughout the walking cycle.
We're now going to talk about a more recent implanted version of a drop foot stimulator called ActiGait, which is implanted surgically in the person's leg. By stimulating the common peroneal nerve, it generates a foot lift and therefore compensates for the interruption in the flow of nerve signals between the person's brain and their motor nerves as a result of stroke. It consists of external electronic components and an implanted electronic system. The control unit is worn at the hip, and a connected antenna is attached to the thigh with an antenna fixture. The implant in the thigh consists of an electronic receiver which sends signals to a cuff electrode on the common peroneal nerve. The timing of the foot lift of dorsiflexion is controlled by a wireless heel switch which is worn on the foot. When the user lifts the foot, the heel switch sends a wireless signal to the waist-worn electronic control unit. The control signals are transmitted from the antenna through the skin to the receiver in the implant. The implant activates the common peroneal nerve, which is located just above the knee. The nerve activates the muscles that are responsible for lifting the foot, resulting in improved walking. There has been an active programme of research at NUI Galway on the design of electrical stimulation systems and their application for over 10 years. The latest system we've developed is called Q-Stim, used to deliver cueing to relieve or prevent a condition called freezing of gait in Parkinson's disease. A block diagram of Q-Stim is shown in the figure. At the centre is the MCU, or microcontroller unit. This is a special type of microprocessor for embedded applications. This is the brain of the stimulator and executes embedded software called firmware. The firmware reads signals from the motion sensing unit, which is comprised of a triaxial accelerometer and a triaxial gyroscope, like you have in your smartphone. The MCU reads these signals to understand the movement patterns of the wearer and thus decide to deliver stimulus using the electrical stimulation unit, which has two stimulation channels which connect to the user using skin surface electrodes. Data from the sensors can also be stored on the SD memory card on the micro SD card unit. The stimulator communicates with a smartphone using the Bluetooth low energy unit, and the user can configure the stimulator for their unique needs using their smartphone and a specially designed app. Then importantly, the whole unit is powered using the power management unit and a rechargeable battery. Freezing of gait, or fog, is defined as a brief episodic absence or marked reduction in forward progression of the feet despite the intention to walk. Persons affected by fog often describe it as if having their feet glued to the ground. In most cases, fog lasts a few seconds, but it can last up to 30 seconds in some cases. The occurrence of fog is triggered by specific situations occurring during walking, such as initiation of walking, turning during walking, walking in a narrow space, walking through doorways, approaching a final destination during walking, or walking in open spaces. Turning during walking is the most common trigger event for fog. Emotional factors such as stress and anxiety can also trigger the occurrence of fog. Fog can give rise to falls and has a major negative impact on the quality of life of those affected. Here we see a photograph of the Q-Stim printed circuit board, or PCB, and the system enclosure. The system was designed in partnership with people with Parkinson's disease, a process called user-centered design, where we sought feedback from persons with Parkinson's disease throughout the design process, and we iterated on our design based on the feedback that we received. In the photograph, we see a person with Parkinson's wearing the unit on a waist-worn pouch. The system has two channels of stimulation, which deliver electrical stimulation via skin surface electrodes worn under the user's clothing. The system is configured and customized to the unique requirements for each user by the user using a specially designed smartphone app with some of the app's screens shown in the image. The app was also designed using a user-centered design approach.